Hello everyone, welcome back. This will be our last video for chapter 19. After this video, there is a chapter 19 addendum, all right, and that will be a different set of videos to accompany this video or the others as well. All right, so looking at the Wittig reaction. Here we can see the formation of alkenes, so carbon-carbon double bonds, if we start with an aldehyde or a ketone. And it all hinges on what having this illide, so this thing right here is spelled Y-L-I-D-E, but it's pronounced illide. And what you have in essence is a negative or partially negative carbon because it is bound to this phosphorus here. You have this triphenyl phosphorus complex that it's attached to. And so in essence, what winds up happening, you can create this illide quite easily, starting with any type of secondary alkyl, any type of secondary alkyl halide, so X here. And so you start with your triphenyl phosphorus here. The lone pair on it will attack the carbonyl carbon, kick off the X. So it's just an SN2 mechanism. And then using a base, anything like sodium hydride, potassium terbutoxide, or butyl lithium, so pretty strong bases, you can throw those in and they'll deprotonate and give you that negatively charged carbon. Now, one thing to recognize, this is one representation you can see where you have a negative carbon, a positive phosphorus, but you can also see a double bond between that phosphorus and carbon as well. So both of those are the same reactive species. All right, so don't get them confused. All right, and so what winds up happening here in the mechanism for our Wittig reaction, once you have your illide, you're going to see negative carbon attacking partial positive carbonyl carbon, and then the pi bond here associating with the oxygen attacks the phosphorus. So you can see this four-membered ring intermediate, this oxyphosphatane. Anyway, it sounds like Tang kicking a glass. Anyway, so then when you have your four-membered ring structure here, what's going to wind up happening, you're going to see the phosphorus and the oxygen are going to stay together. So you're going to break the carbon phosphorus bond, and it's going to donate electrons to make this double bond here, right? That one right there. And then this side over here is going to break the oxygen carbon bond, and we'll get our double bond there. And you can see both E and Z alkene products, all right? And so pretty much if you just notice what winds up happening in all of these, cut the oxygen off, cut the phosphorus off, and then piece these two pieces together, right? Piece these two carbon pieces together, and so you can see what winds up happening here. Same thing here, cut the oxygen off, cut the phosphorus off, piece that aldehyde part and this part together. So you see how you have this three-membered ring, this three-membered chain right up there. All right, very simple stuff. All right. Now, as we saw with that, you can have E and Z products in your alkenes, but if you use the Horner-Wadsworth-Emmons reaction, instead of using an illide, you would actually use a phosphonate ester. And so when you form your phosphonate ester, you're kind of doing something very similar. You're doing this SN2 reaction, where where you're going to see some type of halide, primary halide here, and you're going to kick that off and get the phosphorus there. Now, one thing to pay attention to here, it is OET3, so there's three of these ethoxides on the phosphorus, but now there's only two. All right, and that's because one of those leaves, one of the ethyls, in this case, left to associate with the X. All right, now, what this is saying here is this guy right here will favor E alkene products. And so when you react this phosphonate ester with NaH, right, this is a base, so it's going to specifically deprotonate this carbon here. That's the most acidic carbon that we have, so it's going to deprotonate it. And then you have something that's very similar to a negative carbon, positive phosphorus deal like we saw with Wittig. And then, so what do we see happening here? We're going to kick off the oxygen, kick off the phosphorus, And so that means this phenyl ring and the CH2 here is going to coordinate with this guy here, right? So there's our alkene product that forms. And so you can see variation in what's connected to the phosphorus, but you do want, see here you have a CH2 connected to the phosphorus, and then this stuff changes. So phosphorus, you have a CH2, and then here you have this ester functionality. You can have that as well. So this generic structure can change up a little bit to change what you see in your alkene product. All right. Looking at chemical tests, for anyone who has already looked at the organic 2, some of the organic 2 tests that are in the student project or even scattered throughout some of our other experiments, you have a chemical test for aldehydes and ketones where you use this 2,4, and in that case it's labeled as 2,4-DNPH. Right, but that's dinitrophenylhydrazine test, and if you see an orange precipitate, which is an imine, look at that imine, so cute. So when you see this imine, it is an orange precipitate that forms, and so that's a positive test for ketones and aldehydes. There's also a Tollens test, which is specific to aldehydes, and you use this silver ammonia complex to where you get this carboxylate product, which we're not really going to see in terms of color or anything, but we will see silver solid forming. And actually, this Tollens test is something that is used, it's something very similar, is used to make Christmas ornaments. So if anyone has ever seen those glass balls that they're real shiny, like they have that metallic shininess to them, it's because they have silver coated on the inside of them, and they will literally pour like an aldehyde and this silver complex dissolved in water, but they'll throw it in with peroxide. They'll throw it into a glass ball, stopper it, and then they'll shake it and shake it and shake it and shake it and shake it. And what it does is, as it's producing that silver precipitate, it's getting stuck on the interior of the glass. Because anyway, so that's just random food for thought. All right, and then next up, I know because I did that. I'm not very crafty, but I like silver. Anyway, so looking at aldehydes and ketones in the realm of spectral data that you could see. So with aldehydes and ketones, you do have a carbonyl. So for IR, you're going to be looking for peaks around 1700 inverse centimeters. All right. For proton NMR, the aldehyde proton, so that proton is going to come up somewhere between 9 and 12 ppm. And then if you take this number and multiply it by 20, so 90 times 20 is 180. So 12 times 20 is like 240, right? So if you notice, right, the carbonyl carbons for carbon-13 are this range times 20. All right. So that finishes up chapter 19. Next up will be the addendum for aldehydes and ketones. It's slightly beefy, so get ready for some fun.